Welcome to 23rd lecture on topology. Today's topic is finite difference method to be applied on Reynolds equation, a simplified Reynolds equation. In previous lecture, we learned the benefits of the hybrid approach, proved better approach compared to existing two approaches. Now, today is the time to prove it using some established technique like a finite difference method. Only drawback with finite difference method is that we need to have knowledge of computer programming, and along with that it takes some computational time. Of course, with the increasing power of the computers, it is immaterial now. The few seconds or increase in a few seconds, overall computation time does not matter much. To understand the first finite difference method to be applied for the Reynolds equation, we will start. First slide is the central forward difference method, which we learned in previous lecture, how to apply a central forward difference method. This first term, the first partial term, say pressure variation in x direction, can be represented in central difference method using this formula. Say there is a film thickness at the hypothetical node as a virtual node, I and j we are assuming there are the nodes and their values are integer like 1 1 2 1 2 1 3 1 4, but this is a half node which we are taking as a hypothetical node. As the geometry is known, we can divide geometry any number of nodes without much problem. However, we are doing integer nodes for pressure calculation, and geometry is already known, we can calculate at any distance. So, that is why we are utilizing that half node calculations. So, this is a representing first term. Here we are able to see the p I plus 1, p I minus 1 and p I. Along the x axis, we are taking 3 nodes, this node to be calculated with the help of the remaining 2 nodes. Similarly, we have terms for second term also. We say the central difference method for the second term, second partial term. Here we are getting again, so instead of I we are replacing instead of I we are writing j. I will be silent here. The way in this case we have kept as j without any alteration, j remains same, j in all 3 terms, while in this case j is changing, j plus 0.5, j minus 0.5, and here summation of that j plus 0.5, j minus 0.5. In this case, assumption is that the h is also a function of z, but if h does not depend on the z, then we do not have to write all these terms. We can simply write one term, that is a h I j cube. We do not have to write, we do not have to calculate the half node plus and a half node minus. The simple h I j node, we do not have to really calculate 3 values if h does not depend on the z. And last term is the central difference method. There is a partial derivative of h with respect to s can be simply represented by 2 nodes. The middle node we are not using in this case, here the h plus 1 and h minus 1, and I represent the x direction in this case. So, we require 2 nodes help to evaluate what will be this gradient over here. And when we started finite difference method in a couple of lectures back, we say that we should represent pressure profile or nodal pressure in terms of 4 nodes, as p I j is here, the p I j plus 1, j minus 1, I plus 1 j, I minus 1 j, and this is a rectangular mesh. So, we are taking help of 4 nodes, it is more like taking average of that. And what are these constants? These constants can be figured out by arranging these equations proper order. Whatever the multiplication factor comes on the pressure unit, we think that will be these constants or geometry constant, maybe say a I j, b I j, c I j, d I j, and last will be the source term like this, it will be e I j. Now, if we try to solve it, we need some boundary condition and as well as initial conditions. If nothing is known to us, we by and large we take initial condition as a 0. Pressure at the 0th iteration is 0 at all the nodes. However, if we know the supply pressure, we can use that value, and we know the boundary condition, and if the boundary condition is some finite value, we will put that value, otherwise it will be 0 value. Now, if we substitute those terms which we shown on the previous slide, this overall expression can be represented as something like this. You can see h I plus 0.5 comma j, p I plus 1 j, here h I minus 0.5 comma j, p I minus 1 comma j, and this is a summation of these two film thickness and p I j. Similarly, second term is represented here. Assumption is h is not a function of z. In many problems, it does not really remain a function of z. So, to simplify it, we are just taking it out common term, and then as showing that this h is only calculated at I j node. We are not calculated at any other node in this case. And these are the pressure terms, and this is source term. What we are going to do now, we in this case particularly the denominator was del x bar square, we have simplified it and we taken this side and multiplied over here. So, this is simplified to some extent. It can be further simplified by taking all the summing of all the terms related to p I j, pressure at I j nodes. We know there are term in this p I j terms in the first bracket also, as well as in the second bracket also, and we required value of p I j. That means, we need to take this common or sum of these two terms, and both are the negative. So, we can take it on the right hand side, and right hand side term after summing it becomes something like this: h I plus 1 I plus 0.5 comma j, h I minus 0.5 comma j, and here h I j. All three film thickness the node where we had to calculate pressure, and two other nodes, neighboring nodes, not neighboring nodes, but it is a middle of that is a hypothetically virtual half node. We are summing up and we are calculating like that. Now, we need to find out p I j. So, we can take this on the left hand side, and this multiplication factor, which is depending on the geometry, it does not require any iteration, these are the definite. We know what is the value of these terms. So, we can divide this term, this side we can bring out in the denominator and bring overall expression for p I j. Of course, in this case we are saying the assumption is that film thickness is the only function of x or x bar. Now, after bringing to the left hand side and dividing this whole term, what we get as a multiplication factor for the p I plus 1 j, this complete factor, say h I plus 5 0.5 comma j, h I minus 0.5 comma j, here h I j, and here the difference h I plus 1 and h I minus 1. Now, this is a negative term, this is positive, and this is positive, and this positive, but you can see the multiplication factors. This we know film thickness will decrease as increase with increase in x. That means, this will be negative, h I plus 1 j minus h I minus 1 j, and this film thickness will be greater than this film thickness, then only the conversion will occur, otherwise it will not occur. That means, this term is a negative, negative and negative will be positive. So, overall this term is positive, this term is positive, this term is positive, and this term is positive. Now, we can arrange the way we thought earlier. The p I j should be represented in terms of nodal pressures and with their multiplication factor. So, here a I j is a multiplication factor for p I j plus 1. So, this is factor. Here we are able to see p I j plus 1, and here is a p I j plus 1. So, this factor, whole factor will be equal to a I j. Similarly, for b factor b I j minus 1, here there is this same term p I comma j minus 1, and this multiplication factor will be Bij. Or another word, in a present situation, Aij and Bij are equal, they are same value, they have a same expression. So, I can write Aij like this term, or we can say that Bij also same term, or we can say that instead of Bij I will repeat Aij, write Aij and again here Aij. Similarly, we have Cij, that is a Pi plus 1, here the Pi plus 1 factor comes, and this the pressure term comes over here, and this is the Cij. This is Cij, and here the last term in this case pressure term is a Pi minus 1 j. This is also same Pi minus 1 j, and this factor is d, and this is the last term, that is E, and we are writing in the plus sign. So, when we substitute, we can need to write in accordingly. Either you change this expression something like the hi minus 1 comma j minus hi plus 1 j, and then substitute, or otherwise we can write a computer programming accordingly and get the results. So, this is what we are trying to point out. This Eij is this term. Similarly, Aij and Bij, they are this term, same term, same Aij and Bij are equal. This is Cij term, where we have a number of terms, and Dij is over here. Now, from computational point of view, it is always advisable to non-dimensionalize first, and when non-dimensionalization is happening and both x and z values are the same, like a maximum value at the x axis and y axis and z axis are the same, then we should take the same spacing. Number of nodes in x direction and z direction should be same, because we have non-dimensionalized in such a manner they vary from 0 to 1, they have same values, they have similar kind of magnitude values. So, we should take a equal spacing. If we take a equal spacing, that means del x bar is equal to del x z. What will happen, this term will be simplified, this will be only 1 here, 1 here, 1 here, 1 here, 1 here. So, this number of terms which we need to be counted will be lesser, and we require a spacing only in this source term. Otherwise, all this is a ratio that will be simplified, and calculation will reduce accordingly, and it is preferable. If we are non-dimensionalizing, we should reduce, we should take equal spacing. Of course, if we are not using non-dimensional terms, or we are not non-dimensionalizing the Reynolds equation, in those situation we should take some other spacing, depends on the requirement, depends on the stability possibilities. And another thing which we can observe from these terms are that whenever we are writing h term, and we know very well that it is not varying in the j, or it is not varying in a z direction. So, we can simply drop this j terms, everywhere only the j is appearing, it does not convey any meaning here, like h I plus 0.5, h I minus 0.5. So, its variation is happening in x direction, but j does not remain is remaining constant, it is not changing. We are not writing j plus 1, j minus 1, or j plus 0.5, j minus 0.5 when we are talking about the film thickness. So, we can drop this j index from these terms, that will further simplify the equation, not simplify the equation, but at least the representation will be simplified. We can increase the font size, and there will not be requiring just this j term. So, another thing is that when we are dropping this j from h term, then this constant also will not be requiring j term, because the whole term is representing a, and here if I drop j, after that there is no j at all in this term. So, we can drop this j from Aij also, it will be then only Ai, similarly Bi, Ci, Di and Ei. Here also you can see here the I is only changing, but j is not changing, j can be simply removed, it is not representing anything else, is because there is no variation in z direction which is accounted in the present case. So, we can drop these terms, and with that kind of thing we can see the simplified equation here. H I plus 0.5 j has been removed, H I minus 0.5 j has been removed. Similarly, in this case H I only, j is not there. Again H I plus 0.5 j is not there, H I minus 0.5 is not there, H I is not there. So, this is a slightly simpler equation. When we write computer program, we need to see what kind of arrays are selected. If I write a 2-dimensional array, it will be much costlier compared to 1-dimensional array, and this simplification helps to find out, okay, whether we should go start with 1-dimensional array or 2-dimensional array. Unless if we write these symbols Hij, which is not required, and particularly in this case which is shown that the j is not required. In that case, if I start with a 2-dimensional array, computation time will be more, and anywhere any mistake happens, that is going to impose more and more penalty. So, first think over what is important, and then we should start computational programming on this, right. So, after again as I mentioned that Hij is not required, Hi is maintained, B is maintained, C, I, D, I and E, I, J has been removed completely. However, pressure term we require this J terms, because we can see the variation J minus 1 here, J plus 1 here and J also here. Similarly, I is maintained, I plus 1, I minus 1 and I also. So, we require 2-dimensional array for the pressure term, but we do not require a 2-dimensional array for other term. 1-dimensional array is sufficient to represent these constants, these geometry constant, or which vary as per the geometry, but will not vary as per the dimension iterations, and will not require an iteration. They are definite, we do not require an iteration for this kind of constant calculation. This is again the same representation, so that there should not be any doubt. E has been represented something like this term, A and B represented like this, C representation and this is D representation. And as I mentioned that this is the iteration number 0, and the initial iteration Pij should be equal to 0 if nothing has been given to us. However, sometimes we evaluate pressure profile using some common approach like a hybrid approach. We find out the pressure profile using hybrid approach and evaluate all the nodal pressures, assuming that will give accurate results, and then we start doing iteration. That kind of approach always helpful, because instead of starting from 0, we are writing with some definite value and coming very closer to the actual values. The number of iteration will reduce drastically and solution will be more stable, because starting from 0 there is a possibility of instability. Somewhere solution moves away from the right point and we may not be able to get any convergence. From that point of view, this is important. If you have some good value available, obviously if you are nearly pressure value available to us, and the hybrid approach is one way able to provide those values. Right now, we say that we can make computer program to get the pressure results. So, we should be ready now for a computer program, and this computer program has been written in the MATLAB. I will just transcribe first. See this computer program here, first two lines there is n is E50 and m is E15, but we are talking about suppose there is a x direction and x dimension is given, or we say the x bar is we are using non-dimensional term x bar, so it is a 0 to 1, and we are assuming that there will be a 15 nodes on that, and the spacing can be calculated between based on this, and that spacing is a del x bar in x direction. We know there are 50 nodes, and distance between two nodes will be 1 by n. We know that is minimum value of x bar is 0 and max value is 1. So, 1 minus 0 divided by n is going to give us what will be the spacing in x direction. Similarly, in z direction again we are taking number of nodes 50, As I mentioned, we are believing in equal spacing in z direction and equal spacing in x direction. So, that term has been simplified in equation. This is a C is a clearance. We assuming that for the formula which for the example which you have been quoting for the different kind of approaches, this is a term or radial clearance for 30 micron which we picked up, and here we are also keeping the same thing. We are keeping 30 micron as a clearance, but for the different examples where the C is different, we can use this that different value. However, we want to compare it with the hybrid approach. So, that is why we are taking same example. Hybrid approach results are already available with us, and when we take the same example, we can compare easily. Now, this is dimensions. Now, earlier we were using the word z, the maximum dimension, maximum value of dimension in z direction. Here we are symbolizing it with the z1, because generally x and z are the axis. We do not use those symbols, and it is not very case sensitive, small x and capital X. That is why I use the word z1 and x1. x1 dimension is 10 mm and z1 dimension is 25 mm, which was shown in earlier cases that when we are using the approach 1, it is giving a worse results, or it is not giving as good results as a hybrid approach. But we want to ensure that hybrid approach results are accurate, or at least comparable or better than approach number 1. Now, this is another we are writing the constant 1, that is ratio. We say that the dimension x square divided by z square, which is appearing again and again number of times, and it is not going to vary from iteration to iteration or from node to node. That is why it has been treated as a constant, so that it remains out of the loop. First we calculate, otherwise if we keep this in a loop, it will be again and again calculated, and it will take more time. Maximum number of iterations which we are giving in the past the present case is restricted to 1000, and my experience is that 1000 iterations are more than sufficient. Many times we get it a solution in 30 iterations, 60 iterations, 90 iterations, even the lesser than 100 iterations, but to be on a safer side, I am just keeping it 1000. If the solution is not convergent to the 1000 iterations, then better we recheck the program, something is wrong in the program, otherwise it does not take that much time. Now, this is what we say the initialization of the pressure, if the pressure is not known to us. So, this for loop we can see for I is equal to 1 to n plus 1. Now, there are n divisions. There naturally total nodes will be 51 in this case. So, that is why the 1 to 51. Similarly, in j direction or z direction again is the 1 to 51, and pressure, as I mentioned, nothing is known, we can put equal to 0 to 0.0, that is initialization of the pressure, and it will repeat it till it completes whole matrix, and this is a 2-dimensional array, initialization of pressure using this loop. Now, we need to find out about whether the convergence is happening, iteration over iteration, the solution is improving or not. To indicate that, is why we started at the first iteration, or the 0th iteration in this case particularly, summation is equal to 0. Of course, sum we can write the sum in bracket 0 equal to 0.0, but we are using the integers. So, we started with the 1 and the second iteration will be 2. So, 0th iteration I have time being I have removed is the only first iteration, second iteration, third iteration, and first iteration we do not have any pressure value, all the summation of pressure will be 0, that is shown here. This is an indicator where the overhead every node whatever the pressure will be calculated will be summed up in this, and overall summation will be figured out. That is why there is sum I j. With the nodal pressures we are able to sum up this, will show that it will be repeated in a subsequent other lines, and you can see that this is a loop for the iteration. You see the for iteration for k is equal to k is variable representing the number of iteration, it is varying from 1 to ITER, and ITER is the maximum value 1000. Now, if any time convergence is satisfied, this whole loop will be broken, or it will be where you will there will be some indicator indicates that okay, convergence has happened, you move out of the loop and print the results. So, now the real loop is start over here. You say for I is equal to 2 to n. Keep in mind we are using boundary condition. We know nodal pressure are the first node as well as the n plus 1 node. Initial and final pressure is already known, that is equal to 0, that is equal to ambient pressure. So, using this kind of a loop we are incorporating the boundary condition without any problem. We do not have to calculate, or we do not have to reassign, okay, it is 0, it is 0, it is 0. We say that it is inbuilt 0. Now, you take all those 0 value and account remaining pressure, calculate remaining pressure. That is why the first node and n plus the 1 node is been removed here. We know the pressure at the n plus 1 node and we know the pressure at the 1 node. We do not have to recalculate those. That is why this loop is from I is equal to 2 to n. This is a representation of x bar or calculation of x bar. We know the value of x bar is 0 at the initial and maximum value will be 1.0. So, this index when x I is equal to 0, it should give me the 0 value. Then x I 2, it should give me the del x, x I 3, it should give me the 2 del x, x I 3 as this number increases, that multiplication factor with the del x will increase. This is what has been mentioned over here, has been shown over here. And once we know this x I at x bar pressure or x bar location, we can find out the film thickness, which again we are taking same example which we have quoted earlier for approach 1, approach 2 and hybrid approach. However, if for the common purpose this h will change, if we have some other program other example, the expression for h will be given over here. So, in this case it is h is equal to 2 by 3 2 minus x bar, that is x bar is represented with this. Now, we are requiring h plus 0.5 node and h I minus 0.5 node. So, this is represent h m, h p. h m is for minus 0.5 node and p is for plus 0.5 node. Excuse me. Now, this is what we are representing 2 minus x bar minus 0.5 del x bar. We are subtracting 0.5 node, so the 0.5 spacing, while an h p, which is the positive side, we are saying the plus is the 0.5 del x bar. So, it has been added in this case. However, in addition to that, in source term we required a plus 1 and a minus 1, h I plus 1, h I minus 1. So, that has been represented over here. Say h m I is equal to 2 by 3 2 minus x I minus del x bar. Here the 0.5 is not multiplied, it is a simple 1. So, okay, so it is a h I minus 1 and this will be h I plus 1. We are using this word. So, that now this is calculated in the first iteration. Now, if you want to save really space, we can also remove this whole bracket out of this iterative loop, and we can keep in repeating this with an iteration loop without any alteration. However, for time being I have not done it, assuming that it will be the less subsequent there will be elastic formation or elastic deformation will be considered, then this loop has to come in under iterations. That is why I am maintaining it. Otherwise, if there is no change and there is no elastic deformation calculation, then this loop can simply move out, and then after that subsequent to that only this for loop iteration loop can start. Otherwise, in this case in every iteration this will be calculated again, which is important when we are calculating the elastic deformation with variation in the film thickness because of the pressure. Higher the pressure variation is not going to cause any change in the film thickness. That is why we should not use here, but just for commonality we are maintaining over here. Now, continuation this we have when we were driving the expression, most of the time we have cubic terms. We say the h cube, h I plus minus 0.5 cube and h I plus 0.5 node cubic of that. So, this is a cubic form, and again when we were writing that expression, this term was very constant, it was appearing in almost all of 5 terms, and we can do directly in 5 times, but from computer point of view or saving point of view, once we calculate it, we should repeat it, that will be better. This is our now the constant A, constant B and A are the same. So, B is not been calculated again. Constant C, as we already used that symbol for the clearance, that is why we are writing this new symbol, the C A. Constant D and constant E. Based on this, we can find out what will be the constants. Now, this is x square divided by z square. It was repeated again and again. That is why I say that it should be directly used over here. Similarly, q batch and this constant 2. Constant 2 is, you can see the number of times it has been repeated. Constant 2 here, constant 2, constant 2, and constant 2. That is why we kept only one calculation, and just after that, whatever the answer comes, it should be repeated over here. We should not again and again calculate over. This is the reason why we mentioned like this. So, this is for the I loop. Now, comes the J loop, which is within I loop, it is bracketed in I loop. So, J again we are saying that pressure is 2 to m, we do not require pressure calculation at the first node and the last node, we know already what will be the pressure at those nodes, and this is spacing between the 2 nodes in Z direction, and this is a pressure, nodal pressure, A into P I j plus 1. Here we should write B, but B is equal to A, that is why we are writing A into P I j minus 1. Here instead of writing C, here we are writing C A, as we mentioned clearly, the C is been reserved for the clearance. Then D P I minus 1 j, and last term is a source term, that is E. Now, in earlier slide we showed A I, B I, C I, D I and G I. Now, that can happen that this whole loop can move out of this iterative loop, and then we need to maintain those I terms also. If we are moving out of this, then it has to be written in the first one order array, otherwise there will be problem. However, in this case we are keeping an iteration loop, we do not need to represent this term as an array term. If we move this whole loop out of this iteration, then we require, otherwise we do not require in this case, right. So, pressure has been calculated. Now, we require summation of pressure. Every node will be, pressure will be calculated at every node, and then summation whatever initially we say sum I j is equal to 0, it will be add up in this, and this will continue from let us say 2 to n and 2 to m, and all the pressure terms will be calculated, figure out, summation will be out, and after this final summation of the completion of the both the cycles or both the loops, we can assign this sum as a k plus 1. Iteration 1 is already here, which as I mentioned we are writing a 0 value. So, iteration will be this summation will be 1 plus 1, the 2. So, after first iteration we are getting some 2, and that is equal to this sum I j. Now, we need to find out what will be the percentage error in this calculation. You can simply say absolute value AFC, AFS, sorry, and sum k plus 1 minus sum k, which is already known to us, divided by sum k plus 1. So, this is going to give us what will be the convergence, provided we fix some criteria. Suppose in this case we say this percentage should be lesser than 0.01%. So, that is going to give a convergence criteria. Whenever this summation or this calculation comes out and that is a lesser than this, that shows that okay, the solution has been arrived, or like we are getting a solution and we should break the cycle, and that is the word we say, the break the cycle. If this is there, then break the cycle and end it, and this is a end of if loop, and this is a end of iteration loop. So, this ends the program, this very simple program, and finally, we whatever the pressure we calculated here, we can plot that pressure as a command the surf, which is a 2-dimensional, or obviously gives a 3-dimensional profile, 2-dimensional x and z, and p is height of pressure. and we can find out how many iterations really happened in this whole loop. That can be represented with the number of iteration, maybe say 30, maybe 23, maybe 53. It will come out, and it will show whether the solution is right. Maybe of course, when it is reaching y is equal to 1000, maximum number of iteration means something is wrong, and we should recheck the program. We should find out what is wrong in this program. So, once we have this, we can use our initial data, which we were doing earlier in previous lecture. We quoted in a previous lecture. However, in this case, solution accuracy is reduced. You can say in a program which I show 0.0001, here the solution accuracy we are maintaining as 0.01. What I am trying is something like this. Here we written the percentage should be lesser than 0.0001, and we say in this case we are relaxing it, and we are maintaining that percentage error as a 0.01. Once we do that, we can see the pressure profile which is obtained in this non-dimensional pressure profile obtains something like this. You can see the maximum value is barely 1.2, 1.3 into 10 is to minus 4. Now, if I increase solution accuracy, say instead of 0.01, I want to maintain a solution accuracy as 0.001. Instead of 1% error in a summation, we say 0.1% in error in summation. We find a slight improvement in a maximum value of the pressure, but not that significant improvement. Slight improvement has happened, and the pressure value is increasing to some value. So, slightly a higher value. Now, if we further improve, we say that further reduce error. Instead of 0.1%, we are saying now emphasize on 0.01%. You can see there is some change in this. So, here something was around 1.12 or 1.2 maximum. Here it is reaching roughly 1.4. So, accuracy is improving with improving accuracy, magnitude or pressure magnitude is improving in this case. So, we can say till the saturation comes, whatever, if the further accuracy is increased and we are not changing, we are not getting any variation in the pressure, then we should stop. We said that it has been we have tested accuracy, and convergence is happening with this order. And in this case, particularly what I initially mentioned about what I showed the program previous slide, we started with the n 50 and 50, but just for the comparison purpose, how it vary with number of nodes, I initiated or showed this all three solutions with number of nodes equal to 10 in x direction, 10 in z direction. But to compare with 50 nodes, this second slide shows something like that. Here the number of nodes are 50 in x direction, number of nodes in x direction, as well as z direction 50. I can see that slight change is happening, and but otherwise there is not much variation. This is a straight linear problem, and increasing number of nodes is not going to vary much results. It is not a nonlinear problem. Plumb thickness is also linear variation, and that is why we do not get much significant improvement with increasing number of nodes. But we should try always, if we are getting better results, we should emphasize on that. So, this is what we say the solution accuracy is a 0.001, and number of nodes is 50 into 50, and it is reaching almost the same level as roughly 1.5 over here, maximum value 1.5 into 10 to minus 4. So, we can maintain the same thing. We say that this is a good solution, and it can be compared with now hybrid approach. Now, if you remember when we did a hybrid approach, we also did approach number 1, and for this example we say that when the x is equal to 10 mm and z is equal to 25 mm, we compare for that. In this, for that example, we find the pressure profile that will be the constant or river is the maximum value was around 2.8. Can compare, think of it, 2.8 versus 1.5 or 1.6. This is a huge variation. This is the approach 1. We calculated using the approach 1 by neglecting the second term, and we evaluate the non-dimensional pressure profile. I am talking about the maximum value of pressure profile, maximum value of non-dimensional pressure. that is here in the roughly 1.5, 1.6. So, while here it is coming around 2.8, there is a significant variation. However, compare with our hybrid approach, you can see hybrid approach, of course, these two figures were already shown. So, I am just repeating just for the comparison purpose over here. You can see that maximum value of the pressure coming over 1.8, that is far better than this approach, and we can say it is coming near to this. So, that is why many times we recommend that using this kind of approach will be providing the better results to us. And second thing is that we started at the Pij equal to 0 0. If we are having computer program available and we have we do not have much problem in executing that computer program. So, in that case what we can do, we can estimate the pressure profile using this approach. So, instead of assigning value 0 0, we can assign value this values whatever obtained from the hybrid approach, and subsequent iteration should be done on the finite difference method. It is going to give us better results, overall better results compared to, or much faster results compared to doing only the pressure I j equal to 0 initially. Now, why I am emphasizing here, many times we require a complex solutions, a combination of solutions. So, we have been treating only the hydrodynamic case, where the fluid film is varying with toward the convergence gap, but many times we need to consider whether is there any thickening effect. Increase in the pressure is going to change the viscosity. If that is going to change the viscosity, then we should account that also. And actually some extra efforts will be there, extra calculation will be required. In addition, we know viscosity is a strong function of temperature. Increase in a temperature will happen if there is an increase in a pressure and there is a more friction at the surface. So, that is going to change that is going to change the temperature, and the temperature is going to change the viscosity, and viscosity is going to change the pressure profile. So, they are dependent on each other. That is why when we have this kind of situation, then we require simultaneous solution of equations, and then in that situation, in those situations particularly, anything which is known to us is going to help us a lot. Like in this case, what I am saying that hybrid approach is giving a good pressure profile to us. Better we use that pressure profile as the initial pressure profile for the finite difference method, so that we can achieve overall good results. Now, just to elaborate what I mentioned about the pressure viscosity term is, I am showing this slide here. Is that this is generally viscosity which may initially mention as a constant, but this viscosity can also be represented in terms of the pressure, and this is a pressure viscosity constant, that is roughly value is a 1 into 10 to minus 8, 2 into 10 to minus 8, depends on the which liquid we are using. And this is shown here. The pressure profile is pressure is around 100,000, then multiplier this multiplier particularly e power alpha p is 1. When is increasing 10 times, this is viscosity is increasing by 1%, or multiplier will be 1.01. As further increase in a pressure, this is going to multiplier is going to increase in a value, and a maximum value will occur particularly in this table when we are talking about 10⁹ pressure, or 10⁹ Newton per meter square pressure, that is increasing to 22 times. So, we should use whenever that we know that pressure profile is on the higher side, we should include this kind of effect. Now, once we substitute this, what equation we are going to get is the h cube divided by eta 0, that is a constant viscosity at the ambient pressure, into this factor. Similarly, in this side, and of course, this side there is no viscosity, we can rearrange this equation in something like this. So, now that this is getting a highly nonlinear term. Pressure is already varying in x direction and z direction. In addition, there are nonlinear terms coming over here. There is a multiplication factor, exponential terms are coming over here. That is e power minus alpha and this term. To account this, to simplify this, often use the concept of the reduced pressure. What is the reduced pressure? We say reduced pressure is a q, and q can be represented as a 1 minus exponential minus alpha p divided by alpha. Now, what is the advantage of this assumption? See, when we differentiate it with respect to x, differentiate q with respect to x, what we get? This one is a minus here, it will be 0, minus and minus will be cancelled out. So, e power minus alpha and the pressure gradient in x direction. Same thing, if I differentiate this with respect to z, I am going to get a similar term, e minus e power minus alpha, and this will be dp by dz, and that can be substituted here. So, this is going to give us a simple one. Initially, in for Reynolds equation, without counting this pressure viscosity effect, we were getting the term P, while here we are going to get term Q. That is why we are using the word as a reduced pressure. We have changed the symbol, we have changed the pressure in some other quantity, and but Reynolds equation remains same after this treatment. Now, this is the same equation, almost the same equation as this equation. The only thing is that instead of P, we are writing Q here. So, if I solve this equation, find out the Q and subsequent to that, I can convert to what will be the P, or we can find out what will be the P from this. That means, we are accounting pressure viscosity term without much modification. We just we alter the equation in such a manner this pressure viscosity can be accounted easily. Once it is done, we can find out what will be the results, and we will continue this topic on our next lecture. Thanks for your attention. Thank you.